Good morning, everybody. So today we're going to be doing a couple of review items, mostly around angles, and then we might maybe some new material, maybe review, but finding different measurements of portions of circles, primarily arc length, and then area of a sector. And then we'll be using this later on in tomorrow's lesson to find some more advanced measurements. But today should be pretty quick and simple, so let's just get into it. Um, so just read through this on your own. For most of this portion, what you need to know is that a revolution is 360 degrees when we're talking about degrees, but when we're talking radians, one revolution or a full circle has 2 pi radians. And this is a super important part. It's just because it makes a lot of calculations simpler if we consider this to be the number of radians in a revolution. And it's not just a convenient number. They picked it for a reason. And the reason just makes a lot of calculations within trig and other circle type questions simpler if you do it this way. Since one revolution is 2 pi radians, 180 degrees, or half a revolution would be half that, or pi radians. When we're drawing angles, you need a couple of things. So the first thing, you need the starting or you need the standard position or the starting position basically. And for the most part in this class, it'll be the line going to the right on basically the x-axis. Eventually it'll just look like the x-axis and it'll just be the x-axis. But this is what we usually have as our starting point. The next thing, you want to have another ray over here somewhere coming out of the same point, but we don't know where that spot is until we measure out 225 degrees. So 225 would be 180 plus 45, so 180 degrees, and then halfway between 180 and the next 90. So basically 180 plus 45. And this is what any angle should look like if it's not in a shape. So 2 rays starting at the same vertex with the angle being marked. And the reason for that is there really could be an infinite number of angles that fit into this scenario. So you just want to tell people what you're working with. With radians, you have to think about portions of the circle basically. This is 2/3 of 180 because pi is 180 degrees. So think about that. But this negative sign means something. I forgot to mention this, but if it's a positive angle, you're going counterclockwise. If it's a negative angle, you're going to go clockwise. So this would be pi over 2. This would be pi. So somewhere in between, doesn't have to be perfect. Should be 2 pi over 3. This is probably a little off. Probably should be closer to that. But that's just because this should be 2/3 of this straight line. All right. 630 degrees. That is going to be more than one revolution. So this is why those arcs matter when we get into this. That way someone knows that you've gone over a full revolution. So I count them out. This is 360. And then from here, I know it's not going to be another full revolution because it's under 720. So I count out by 90s until I get there or get close. So 360 plus 90 is 450, 540, and then 540 plus 90 is 630. So it'll be right there. And then pi over 4, this is positive. So again, we're going to go clockwise or counterclockwise. This is a fourth of 180. So 90 is a half of 180. So a fourth would be halfway between there. Sorry. Converting between degrees and radians. The key here is you have to know the portion between the two. So taking this portion, you should be able to create a ratio comparing the two. Think about converting units. So degrees, we want to convert degrees by multiplying, or we want to divide it by degrees. If we divide by degrees, degrees cancel. So those go away. And then we want to multiply by the number of radians in that form. So from here, it's just simplifying the fraction. 60 divided by 180 is 1/3. So this is 1/3 of pi, or pi over 3. Next, negative 330. Again, degrees to radians. You want to multiply by the same ratio, pi over 180. And you don't have to deal with those units every single time. I was just showing you why you're choosing this route. Again, simplify the fraction. So this is 330 over 180 times pi. So I would just I would divide by that 10, get it out of there. And then simplify this fraction. 3 goes into both of those. So this would be 11, and this would be 6, or negative 11 pi over 6. And that's radians. We're working with radians now, so we want to cancel the radians and get it into degrees. You're going to use the reciprocal of this ratio. That way the radians are in the bottom, and the radians can cancel with radians. And 180 degrees would be left. Most of the time, if there's pi in there, it means that it's going to be in radians. This is not always the case, just keep that in mind. But if you see a pi, generally you're doing this conversion, generally you want to get rid of it. Radians don't have to have pi in it. Degrees can have pi in it. Just be careful. You're not just assuming, since there's pi or not pi, that it's degrees or radians. Doesn't have to be. You could have 1 radian, not 1 pi radians, and it's completely fine. Again, simplify the fraction. 180 divided by 6 is 30, and then 30 times 5 is 150. So 150 degrees. Last, we have negative 3 pi over 2. You're going to multiply it by, we're trying to get rid of radians, so we want to divide by radians, multiply by degrees. Pi's cancel. 180 divided by 2 is 90. 90 times negative 3 is negative 270. There you have it. Biggest thing that we need, radians is going to make a lot of calculations simpler. So for the most part, we're going to be using radians in this class. Just be ready to convert between the two. Pretty soon you'll get the hang of it, and you'll just know that, hey, that's part of a circle, and that correlates with this angle measurement. Many of the degrees will be just more complicated because it's not set up for you to make quick calculations like radians are. With these two formulas, arc length and area sector, it uses this Greek letter theta. Theta we use for angles, and primarily angles that are written as radians. Doesn't have to be, but most of the time these are. In this case, theta has to be in radians. So both of these formulas do not work when they're in degrees. For number 4, this creates an issue. So we have to make sure that our angle's written in radians, otherwise these formulas don't do anything for us. But arc length is essentially just trying to figure out the perimeter of the portion of the circle. So you're just trying to figure out how far, say, if we have a full circle, how far are these 2 points from each other if we know the angle in between. If we know the angle and we know the radius, we can figure out this length. You don't need a formula to do this, just like most of math. You don't need a formula, but the formula is super simple if it's in radians. So S, I don't know why we use S for arc length. Doesn't really make sense, but there we have it. S is equal to radius times theta. For an area of a sector, it's going to be A for area 1/2 r squared theta. This one, both of these, if you just said, okay, what if theta is the full circle? If I plug in 2 pi here, S is now the circumference, so circumference is 2 pi r, which is a normal calculation for us. Another reason why we use 2 pi for a full revolution is just so these formulas are quick and simple. Just plug in the number of radians, you're good to go. If you plug in 2 pi here, 1/2 times 2 pi times r squared, well, the 1/2 times the 2 cancel, so the area of a full circle would just be pi r squared. So again, this works for all cases, and it's just coming from the 2 formulas of a circle that we have, circumference and area. If you didn't care about that, then let's move on to just the questions. So arc length is S. It wants to find the arc length of a circle with radius of 2 and radians, or a central angle of 0.25 radians. Careful, this is not 0.25 pi radians. This is just 0.25 radians. Do not plug in a pi there, just 0.25. So to find the arc length, you just need to multiply these two out. 2 times 1/4 is 1/2, so this is 1/2 meters. Arc length will be linear measurements, so meters, where area is going to be square measurements, so might be, in this case, it'll be square feet. The area of a sector is 1/2 times r squared. R is 2. And then I'm going to save this for a second, because right now our central angle is 30 degrees. We need it in radians, so let's convert that. 30 divided by 180 is a sixth, so pi over 6, and plug that in. All right, 4 divided by 2 is 2, so this is 2 pi over 6, or pi over 3, which looks like an angle. It's not an angle, it's the area. So just make sure you use correct units, feet squared. So pi over 3 feet squared. If you were to do that division, it's a little bit over 1, so a little over 1 square foot. All right, using those formulas, we're just going to find those missing values. So we have S equals r theta for the formula we want to use. We know theta is 1/3. We don't know r. We know that S is 2. Solve for r, multiply by 3, you get that r is 6. Find theta, so A equals 1/2 r squared theta. A is 8. So 8, beautiful 8, equals 1/2 r squared theta. This is 36 times 1/2 is 18. So 18 theta equals 8. Divide both sides by 18. You get that theta is 8/18, or 4/9. All right, that's it for today. Now go through My Open Math. Make sure you answer as many questions as you can in the 30 minutes. If you're doing the College Now credit, make sure you're doing the whole thing. I don't know how long this video is, but whatever this video is, take that away from 30 minutes. Use that remaining time to go through as many MyOpenMath questions as you can, and then make sure you turn in the assignment to show me that you've done your 30 minutes. Okay, till next time.